You may know the theory of rainfall runoff processes. You may have worked with model parameters and even used industry standard tools. But have you ever looked at how these models actually work behind the scenes? In this video, we build a simple rainfall runoff model from scratch using the SCS Curve Number method and the Unit Hydrograph approach, the same core setup used in tools like HEC-HMS. The SCS method was developed by the US Soil Conservation Service between the 1950s and 1970s based on rainfall runoff observations from small agricultural catchments. It's an empirical approach that links rainfall to runoff using a single parameter, the curve number or CN. Following the water balance equation, the method assumes total rainfall is partitioned into initial abstraction IA, infiltration F, and runoff Q. The model also relies on an important assumption known as proportionality assumption as shown below. Here, S is the potential maximum retention. To derive the runoff equation in this method, we first substitute equation 1, the water balance, into equation 2, the proportionality assumption. By cross-multiplying and solving for Q, we get this. We can now have the final SCS runoff equation like this. On the other hand, the potential maximum retention S is calculated using the most important model parameter known as curve number. CN ranges between 0 to 100. A CN of 100 represents an impervious surface, while a CN of 0 represents an infinite retention. Typical range for CN is between 40 to 95 for natural watersheds. CN generally depends on hydrologic soil group, land use or cover, hydrological condition, and antecedent moisture condition. Now let's get back to initial abstraction, IA. Originally, the SCS method assumed IA is 0.2 times S. This implies that 20% of potential retention must be satisfied before runoff begins. However, recent research suggests IA over S may be lower for many watersheds, so this can be treated as a calibration parameter. The limitations of SCS method are as follows. First, being an empirical relationship. Second, it assumes a spatially uniform rainfall and watershed properties. Third, CN selection is subjective for complex land uses. And finally, it may not perform well for very large or very small events. Now let's move to unit hydrograph theory. A unit hydrograph is the direct runoff hydrograph resulting from one unit of effective rainfall produced uniformly over the watershed at a constant rate during a specified duration. Key principles are as follows. First, linearity. Response is proportional to input. Second, time invariance. Response doesn't change with time. Third, superposition. Response to multiple inputs equal to sum of individual responses. The unit hydrograph method also relies on convolution, the process of computing total runoff from effective rainfall using the unit hydrograph. For discrete time steps, this can be calculated as follows. While actual unit hydrograph shapes vary, a triangular approximation provides a simple, reasonable representation. The volume under the unit hydrograph must equal 1 unit of effective rainfall over the watershed area. For triangular unit hydrograph, runoff volume can be calculated like this. On the other hand, volume equals the catchment area times 1 unit of effective rainfall. Therefore, runoff peak or QP can be calculated like this. Alternatively, SCS method suggests an empirical relationship for this, where C is a constant depending on units. Note that time to peak can be estimated from this equation, where delta T is the duration of effective rainfall and T lag is the lag time from center of mass of effective rainfall to peak runoff. For a small agricultural watershed, SCS suggests T lag equal to 0.6 times TC, where TC is the time of concentration, the time for water to travel from the hydraulically most distant point to the outlet. If you want to learn more about TC and different methods for estimating it, please watch our video on this topic. Combining the SCS Curve Number method and the unit hydrograph is the default configuration for basic hydrological studies in many industry standard software packages such as HEC-HMS. This approach separates the rainfall runoff process into two key components, losses and transformation. In this exercise, we first convert rainfall into effective rainfall using the SCS Curve Number method, accounting for losses such as initial abstraction and infiltration. Then, we transform the effective rainfall into a runoff hydrograph using the unit hydrograph approach, applying convolution principles. Finally, we compare simulated and observed hydrographs, evaluate model performance using key performance metrics, and adjust model parameters such as curve number and unit hydrograph characteristics to improve the fit. Now that we have covered the theoretical foundation, let's move into Excel and put everything into practice. Well, in our example, rainfall and observed runoff are provided. So as you can see, we have a 14-hour rainfall event, and for that one, the observed runoff is going all the way down to roughly 40 hours. I have plotted that. It's a nice bell-shaped hydrograph that we are going to simulate. The other information that is provided to us is the drainage area or the catchment area. It's 25 square kilometer. The time step is hourly, so I have 1 hour, and then the rainfall duration, as I stated earlier, is 14 hours. In this example, I have considered 3 calibration parameters. The first one is of course curve number. The second one is the lag in hours. The third calibration parameter is lambda, initial abstraction over the potential maximum retention. The typical value for that is 0.2, but we mentioned earlier that in recent research, the recommended values are between 0.05 to 0.15, but I've already given the range of 0.05 to 0.2. So now we move to calculated variables. We start with S, the potential maximum retention. That will be based on the curve number. So I follow this equation that I have already put in Excel. The second one is going to be IA, which will be simply lambda times our S value following this ratio. The next important parameter is TP in hours, and for that one I'm following this formula, delta T over T, which is the duration of rain divided by 2 plus T lag. After that, I find the base of the hydrograph following this formula. And then the last one is of course the peak discharge, and that will be C, a coefficient which is related to the unit conversion, multiplied to the area divided by TP. Our C here is 0.208. To give a bit of context about what we want to do in this example, please note that here we have 2 components. The first one is using the SCS curve number method in order to get the effective rainfall. And for that one, I have the S and IA, and of course the curve number as the key parameters. And then on the other hand, we have the unit hydrograph that are working with the lag value and of course the TB, QP and TP. Now I move to the second sheet of this Excel spreadsheet. So here I'm going to develop the unit hydrograph calculation. So let's have a quick review of what we want to do here. So far we have calculated the QP. So I have the QP value. I also know what is the TP, and also I know what is the TB, the base of the hydrograph. So what I'm going to do is a simple math. In order to find the ordinates of the unit hydrograph, what I'm going to do is developing 2 straight lines. So the rising limb is basically a simple line that follows this equation. The ordinate that I want is going to be the slope, which is QP divided by time TP multiplied to the time ordinate. So it's very simple to find that one. But when I pass the peak, I have a declining line. So the equation will be like this. Y, which is the unit hydrograph ordinate, is equal to QP divided by the base minus peak time multiplied to TB minus T, which is the time. So what I'm going to do now is just simply put it in an equation in Excel, which I've already done. So it is going to be the if function. So what I'm going to say is that if the time is smaller than the time to peak, so that will be simply following the first line that I've put it here. So it's the same equation, dividing the peak over the time to peak, and of course multiplying that to the time that I have. And in case if I pass the TP, which means the second line, that's the next equation. So here it says that what I need to do is basically following this equation. Don't get confused, I'm still using this one, but it says A3 is smaller than TB. So because we know that when we come to this condition, we have already passed the TB. What I need to know is, am I exceeding the base or not? So if not, I calculate the ordinate. If yes, I need to put 0. In other words, when I pass the TB, the ordinate of the unit hydrograph is going to be 0. Applying this formula is going to give me the ordinates of the unit hydrograph, as you can see here. So the next sheet is basically going to do 2 things for us. First, I'm going to generate the effective rainfall values using the curve number method, and then I apply that into the unit hydrograph process in order to generate the final hydrograph of our model. So just to give a bit of context, we know that if our cumulative rain is smaller than the initial abstraction, I'm going to have basically 0 effective rain. And once our initial abstraction gets satisfied, in other words means P larger than IA, then I should be able to calculate my cumulative effective rainfall using the formula that we just developed earlier. So what I'm going to do in Excel is basically following this procedure. And don't forget, we are playing with the cumulative values of rain, but of course at the end we can convert it into the individual time step values. So let's do that here in Excel. In the first column I have time, in the second one is the rainfall, the one that is given to us in the question. And then after that I create the cumulative rainfall. In other words, each cell is adding up the rainfall value one by one. And then I need to go for cumulative effective rainfall. And that's the part that formula that I just explained earlier is coming to place. So if my cumulative rain larger than the initial abstraction, I will follow the equation. If not, means that it is consumed by the initial abstraction and I shouldn't get any runoff, or the value will be 0. So I create that, as you can see here. And then after that, I can convert it back into incremental values, or the effective rain for each individual time step. So what I'm going to do is very simple. For the first one, the incremental one is the first cumulative, but in the second, I will actually deduct it from the previous value. So my D4 minus D3 is giving me this number, and so on. So in other words, as an example here, this value is created by deducting 3.8 from 0.25. So this will give me the hydrograph of the effective rain, or the food to our unit hydrograph process. So here we go for convolution. So what we do is quite straightforward. I have a hydrograph and I need to multiply every single cell of this hydrograph into the ordinates of unit hydrograph. So it's done here. So as you can see, my E3, I fixed the value because I want to drag it, multiply to the ordinate of the unit hydrograph, which is provided here in the previous sheet. So B3, this one becomes B4, and so on. And when I go to the second value of my effective rain, I do the same thing. I multiply that to the unit hydrograph ordinates, but I need to have one step time shift, and that's the procedure of convolution. So the yellow one means that I leave one cell and I start the whole thing from here. Practically, I repeat the same process that I did in the previous column, starting from second cell, and I need to repeat the same process by leaving more cells empty. So for example, for this one I leave 2 cells, 3 cells, and 4. And as you can see, since my first 7 values are 0, basically from PE0 to PE6 means 7 columns are going to be all zeros, because I multiply 0 to ordinates of the unit hydrograph and I get nothing. But starting from this cell, the values are going to be generated. Where do we stop? Generally when we get 0 again. That means that basically my last few columns are not necessary, but I put it there because at first I didn't know what values I will get. So after completing this process, the final hydrograph, or the simulated hydrograph that we are after, is going to be the summation of the rows of the unit hydrograph calculation. So practically this cell is the summation from column F all the way to column Y, and we repeat it for the whole thing, and that is going to be the end of simulation. So now we move to the next step, which means comparing the simulated hydrograph with the observed one, look at the performance, and then start to playing with the parameters. And don't forget, I just put some dummy values at first to just build the model. Now I'm going to do sensitivity test in order to see how the model reacts to the change of parameters. So to initiate the process, I have put 3 calibration parameters within the range that I have provided. So for example, my curve number, I put 50 to just start with, the lag of 2 hours, and the lambda of 0.2. And now we go to the results sheet. So here I have the observed versus the simulated ones to compare. I have plotted them. As you can see, my observed runoff, the blue one, is much higher. So our model is underestimating. What I have done also as the performance metrics, I have the NSE value, MAE, and of course I go for the peak estimation. So I have the peak bias and time to peak error. And the p-bias is also provided in order to tell us what is the volume estimation. So as you can see, the model performance at this stage is not that good because I just randomly put some numbers. So now let's go back to the inputs and play around with the parameters. So I start with curve number. We know that if I increase the curve number, I'm reducing the S, and that means that I create more runoff. And in our case, I think I need to do so because we just saw that the simulated hydrograph for the current value of CN is underestimating the observed hydrograph. So let me increase that, let's say, to 60 and see the immediate impact of that on our result. So if I go back, I can see that the peak is coming up, so the performance is better. I can again increase it a bit more, for example, bring it to 70, and what I'm going to see is that now is overestimating. That means that the right value should be somewhere in between. Let's have a look on the other parameters. We have a relatively unsatisfactory p-bias, obviously because of the overestimation. The peak estimation also is not that good. 20% is a bit large. Time to peak error is good, and our NSE is relatively good as well. So let's go back to the other parameters. Okay, now what about the second parameter? The second parameter, lag, is basically affecting our time to peak, and that means that we are affecting the Q peak as well as the base of our hydrograph. So by reducing that, I'm reducing TP, and obviously I'm increasing the peak. So let's do that. For example, if I drop it to 1, we can simply see that our hydrograph gets larger, and our p-bias, p-flow bias, which last time was 20%, now is going to 32%, and our NSE is also dropping from 0.80 something to 0.72. So the third parameter is lambda, and at the moment I have put the maximum possible value from the range. Let's see if I reduce it, what is going to happen to the systems. So as you can see, the things are even worse. Our peak error now is 50%. Now I have got some error in time. So our simulated peak arrives 2 hours earlier, and also our NSE is even worse. Looking at p-bias, we can see that it is not good as well. So 55% is generally a very large p-bias. Instead of randomly playing with the calibration parameters, we can use the optimization methods available in Excel. So here what I'm going to do is defining an objective function. So I go back to the results. So it is always good to have an objective function that mixes a couple of performance metrics. What I normally do is mixing a PFB as a representative for peak estimation, a p-bias for the volumes, and also I put MAE, which is looking at the overall errors on the individual ordinates of the hydrograph. I normally don't put TPE. We can optimize the parameters and check on that, and if necessary, then we do a bit of like manual changes on the model parameters. And also I don't include NSE in this mix objective function. The reason is that PFB, p-bias, and MAE are error parameters, and NSE is an efficiency, and mixing them needs a bit of careful arrangements. Let's start to define our objective function here. I'm going to multiply the 3 error parameters, and since some of them may have positive or negative signs, I'm going to use absolute function to cancel those in order to avoid confusing our objective function. So absolute of, I go to the result sheet, I choose the peak error, multiply to p-bias, multiply to MAE. So this is the objective function that I have, and I want to minimize it because these are 3 errors multiplying to each other, and the best is to bring them down as much as possible to 0. So after that, look at the data tab in your Excel. There is a solver item here. If you don't see it, that means that it's not activated. You need to go to the file, and under option you can activate that. So click on solver. So the first thing is I need to select the cell that I want to optimize. In our case is this one, G4. I want to minimize it. Sometimes you may define an objective function that needs to be maximized, but in our case we have errors, so it should be minimized. Then in this tab, you need to fill those cells that need to be calibrated. Here I have chosen B12, 13, and 14, means CN, lag, and lambda. And then after that, I define the constraints. So the constraints are the ranges that I have for the parameters. How do we do that? It's very simple. You just click on the add, and you can introduce what cell, what condition you want to put, and of course a value, which I've already done that. Once ready, you click on the solve, and very quickly that is going to be done for you. So these are the set of parameters that I've got. The objective function has got a very small value that shows a very good performance, but let's look at the result. So I go to the result, I can see that I have the NSE of 0.95, which is perfect. The error of the peak is very small, it's close to 0, so it's a perfect. P-bias is also perfect. Generally anything below 5-10% is really good. The only issue we have is the TPE of -1, which is the time error. We want to see whether it is possible to play around with the other parameters and perhaps adjust that. There are two important points to mention. The first one is be careful about the equifinality. That means that different set of parameters may give us a relatively similar results. You need to be careful that the numbers that the optimizer provides to you are meaningful to your catchment. For example, based on the land use, you may have some ideas about the potential range of your CN. And that means if the number that the solver provides to you is off that limit, that means that it's not acceptable. So it's always good to narrow down the range to the acceptable values. The second point is about the fact that the solver in Excel basically converges to the values that are closer to the numbers that are available to start with. So for example, in our case, if you remember, I had some dummy numbers here, and solver starts from that point to search for the optimized value. That means if I change that, that will converge to a different set of calibrated parameters. So in order to show that, what I'm going to do, I just copy these values, keep it here as a reference for myself. And then what I'm going to do, I'm changing the initial values here. Let's say I increase this one to 70. This one I go to, let's say 2. And this one I put a 0.2. And I go here, click on the solver again and solve it one more time. So same thing, I'm not changing anything, I just solve it. And as you can see now, I get a totally different set of parameters. So last time we had curve number of 57, now we have 62. Time lag was 1, now is 1.9. And the value that we got as 0.1 for the lambda is now 0.2. So let's have a look on the results. If I go there, I can see that now I've got a perfect timing. My NSE is still very good. Peak error is a bit worse, but it's still acceptable. And my P-bias is much better than last time. So it's acceptable. So this set of parameters is also reasonable. And I would prefer this one because I have a better peak timing, and perhaps that underestimation can be adjusted manually. So as I know, by increasing the CN, I'm going to increase the peak. Let's say I increase this number, and of course I need to understand that this may affect the P-bias. So last time we had a perfect volume, but let's say I'm here more interested in the peak. So I slightly increase this number to, let's say, 65, and then I go back to the results and I can see that now I have a much better peak estimation. The TP is still good. My P-bias is affected. Last time was smaller, but now still is in the satisfactory level. And my NSE is also still a very good number, close to 0.98. So I have optimized my parameters for the scenario that I'm more interested in a better peak estimation, both timing and the value. Even with a relatively simple rainfall runoff framework like SCS and Unit Hydrograph, parameter choices, assumptions, and interpretations matter. And tools like Excel can be incredibly helpful for learning, testing ideas, and developing intuition about model behavior. If you found this video helpful, please share it with others and stay tuned for more videos like this. Thank you for watching. See you in the next one.